Welcome back. Here is Metaforming 3 Part 2. We're going to look into the last process, which is the flashless forging. Flashless forging is a process where the compression of work in the punch and die where the cavity does not allow for flash. So meaning that the volume for the workpiece before the compression process must be the same for the final one. So the starting work volume must be equal in order to make sure the tool is protected. If not, then the work material and also the flash will and the die will be broken. So process control more demanding than the impression die forging because it is more into the precision forging. So it is best suited for part geometry that are simple and symmetrical, and it is also classified as precision forging process. Now let us look into the process. Here are the diagram showing the flashless forging. So this is the condition where the die here they have a complete closed area over here. The work material will be placed in the middle part, and then it will be punched. Okay, and then this is partial compression. If you can see, the work material will start bulging and filling the cavity, and then in the end it will be complete by filling all the area inside the cavity. So this one is just a simple one. As for the flashless forging, you can also create a certain design, but it's supposed to be simpler compared to the impression die forging. For the classification of the forging operation can be done in two classification. One is in terms of the work temperature, and another one is on the whether it is impact of press forging. Okay, so for cold versus hot forging, hot or warm forging, the advantages will be in the reduction of the strength. So then it will increase the ductility of the work material, so it will be easier for the forging operation to take place. For cold forging, the advantages will be increased strength due to the strain hardening, but the work material must be ductile enough to be forged. If not, then you will break the die, or the workpiece itself will be broken. And another one is impact of press forging. For forging hammer, it apply an impact forge, so it's going to be a very huge forces. And then forging press, so it apply gradual forces. Let us look into the forging hammers. So for forging hammers, it apply impact load against work parts through two types. First is through gravity drop hammer. So the impact energy will be from the falling weight of the heavy ram. And another one is the power drop hammer, where it accelerates the ram by pressurized air or steam. The disadvantages of the forging hammer will be the impact energy that will be transmitted through the anvil into the floor of the building. So this is not a healthy work environment for the workers. So it is commonly used for impression die forging. The picture here showing the diagram on the detail of the drop hammer for impression die forging. If you can see, this is the head, this is the piston rod, and then there are frame working here, and there are anvil on the bottom, and this is the ram. So this is how where the hammering happen. Okay, so this is why the forces will go will give the vibration to the anvil, and then it will transmit it to the floor, which is not good. In the other hand, forging press will apply gradual pressure to accomplish the compression operation. So there are three methods to achieve the forging press. There are mechanical press. This one, it will convert rotation of the drive motor into linear motion of ram. Second, using the hydraulic press. So this one, of course, using hydraulic piston to actuate the ram. And the last one is screw press, where the screw mechanism will drive the ram. Let us look into the picture on this operation. So here are the comparison for all type of the forging machine. So the first one is the drop hammer. If you can see, this is the ram. What happened is all the ram here will go up, and then it will be released, and then using the weight of the ram, it will hit into the workpiece. Okay, so for the screw press, there will be a flywheels and also so that and screw, so that when this screw is being rotated, so that it will gradually give forces to this part. Okay, and the next one is crank press, which is the mechanical part. Okay, mechanical press. So this one is using the crank shaft mechanism, where when it is rotate, it will gradually give pressure to the workpiece in rotational way, meaning that it give once it's moving, it give press and then it release and then it give press again. Okay, so the next one will be the hydraulic press. So for the hydraulic press, this one is given by the hydraulic pressure here, so then it will give the pressure, the press gradually to the work part in here. So here we are showing the differences, of course, because this is just an animation. In the real world, forming a hammer will be faster and will be bigger in terms of the pressure given. Okay, so this is how the forging press. So it is done slowly, so that until you get all the final shape. Now let us look into other operations related to the forging process. The next process will be upsetting and heating, where the forging process used to form the head on the nail, bowl, and similar hardware products. So in this process, more part produced by upsetting than any other forging operation. So it perform either cold, warm, or hot, and the machine called heater or former. So wire or bar stock is fed into the machine, and then the end will be punch, okay, to get the bowl and the head of the bowl. Okay, so the thread rolling is then used to form the thread. So I'm going to give you the link to the video on how the bowl and nuts are created. So here is the process. Okay, so if you can see here, the starting material, which is the wire stock, will be fed to the stop here. Okay, and then when it's already stopped, the part here the die will grip the wire stock here, and then the stock will retract. The stock will go up, and then the punch will move forward and punch into the head part here. So then the bottom it will create the head of the nail or the part. Here are some other example on how the heating process is being done. So if you can see, this one is by punching to get the head of a nail using the open die. Okay, so there are no closed area over here. Okay, so then you will get the nail head over like this, and then round head formed by the punch. So the punch is designed to get the shape of the round head like this one, and then this is the head style, where this is the countersink, and then this is the hexagon shape, and then this is the another type of nail. Okay, so there are also the link. This is the link to show the how the upsetting process is done for the bowl and nuts. Okay, so take a look into this one to see the real process on how the process is being performed. There are also explanation on the each step of the process. The next process we are looking into is swagging. Swagging is a rotating die where it hammer the workpiece radially. So previously we only see the open die forging and the one that create the shape, a certain shape, right? So for this one, swagging is particularly only for the radial part, where you want to create want to reduce the diameter of the workpiece. So this one is used to reduce the diameter of tube or solid rod stock and usually mandrel are required to control the shape and the size of the internal diameter of the tubular part. This process showing of the illustration of the swagging process. So if you can see, this is the die. So in this area, in this process, not only the die will be moving up and down, and it will also rotating. So in order to maintain the diameter of the work part, if it is only moving on one surface like this one, so that the diameter will not be uniform on all area. So that's why in swagging, both the die will be moving up and down and also rotating in the same time. So here is the illustration showing the how the swagging process happens. So actually it is moving in rotation, rotated like this one. This one is just to show the focus. Okay, so not only it is rotating, it is also moving up and down to reduce the diameter of the workpiece. You can look into the swagging process in the link given at the bottom. So the last process is trimming. So this trimming process is a cutting operation to remove the flash from the work part in impression die forging. You can also see in the video in the previous impression die forging, I've already attached the link to the process. Usually the part will be placed on these cutting edges. Okay, and then it will be punched, and then it will be the part will go down here, and the remaining will be on the die here. Okay, so after that you just remove the flash, and then you can get the final product. Now let us look into the problem. A cool heading operation from the head of a steel nail. So the strength coefficient of the steel is 500 MPa and the strain hardening exponent equal to 0.22. So the coefficient of friction at the die work interface is 0.14. So the diameter of the wire stop for the nail is 4.0 mm. The nail head diameter is 10 and thickness is 1.5 mm. The final length of the nail equal to 60 mm. So here they want what length of stock must project out of the die in order to provide sufficient volume of work material for this upsetting operation. Okay, so it looks very confusing, right? So the actually it is very easy. If you go into this part here, so we want to understand what they want actually. So if we I'm going to show you the illustration. Sorry for my drawing, it is not that good. Okay, so they want to know how much is the work material that's supposed to be coming out here, right? So before you do the process of heading, okay, so the first thing that first we have to know what will be the final volume of the heel knit. Okay, so if we can see the volume calculation, so volume for the head will be pi d squared times the h final over the 4. Okay, this one is just the normal volume calculation for the circle like this. Okay, for the head. Okay, so this is the calculation for the volume. Okay, so since we already have the value for the final, so d squared is given by here 10 mm. HF thickness will be 1.5, and then divide by 4. So then you will get the final volume will be 117.8 mm cube. Okay, so then what we have to do is cross-sectional area of wire stop. Okay, the initial one, what will be the cross-sectional area. So this one is the calculation for the area. A equal to pi d squared over 4. So then you will get the area, right? Cross-sectional area. So it is given the wire stock diameter is 4.0 mm. Okay, So then we just put the value here, so you will get the area here. Okay, so now do you remember the calculation for volume? Volume equal to area times the in term of the usually is the width or the thickness, right? So as for this one is the height. Okay, the volume is cross-sectional area times h here, right? Okay, since we already have the volume, the final volume, and we also know the cross-sectional area, so what you have to do is h naught equal to volume over A. Then you will get the calculation for the value of h naught. So it is given 117.8 divided by the A naught, then you will get the final height, the initial height that you want to have. Okay, so that the A. So now we go for the B. Compute the maximum force that the punch must apply to form the head in the open die operation. Okay, it's already given open die operation. So if you go back to the open die operation, F equal to KF, what is it? YF A, right? Remember this one? Okay, so now we already have the A. What we don't have here is the K and also the YF, KF and YF. So YF is calculated by 500 times epsilon, right? So epsilon, you have to calculate the epsilon first, equal to load 9.737 divided by 1.5. So how is this come up? If you go back here, so the initial height is 9.37, the final one is 1.5 mm, right? So then you'll get the epsilon value equal to 1.83. So then when you put it inside the YF equation, you're going to get 571 MPa. And then for the area for the final will be pi d squared over 4, so you'll get 78.5 mm squared. So then KF is 1 plus 0.4, okay, times the 0.14, and that this one you can refer to the equation again, KF equal to 1 plus 0.4, I don't remember. Okay, so you refer to the equation again for this one. Okay, when you fill in all the value inside here, and then you will be able to calculate the F using the value that you already calculate. Okay, so here is another question. You can try it on your own. This one is, for example, this one yield point is already given where the strain is 0.002. This is the condition where high is given is 35 and high is given 30. Here is the solution. If you look into the solution, actually it is the same method is being used. It is involved the volume, and then it involved the calculation of the area, and then you can get the KF, and then you can calculate the F value. Okay, so everything is just following the step of using the equation given. Okay, so you can just try it on this part. Try to solve it. If you have any problem on understanding, you can always contact me. Okay, so here's the end of the part 3 metal forming. Thank you for listening. Assalamualaikum.